let's talk a little bit more about binary numbers. And I want to frame this in a way where it relates to our normal number system, the decimal number system. So when we count, we are using decimal, which is base 10. And what that means is that there are 10 different symbols in this number system, 0 through 9. So I only have 10 different symbols to represent an infinite amount of numbers, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And when I run out of those symbols, I have to use place values to continue counting. And so when we talk about binary, we are talking about a base 2 number system. And so there are two different symbols in this number system, just 0 and 1. And so we can use this base system to represent any number that we want using just zeros and ones. And because computers only can store zeros and ones, that's why we have to represent everything in binary in a computer. Okay, so when we count in decimal, we start out with one place, right? And when we run out of those symbols, we add another place value. So if I count, I start at 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I've used all my symbols, right? 0 through 9. So I'm going to start over in the first place, but then I'm going to add another symbol in the second place. So I'm going to start over at 0, and then I'm going to go to the next symbol, 1. So that's how we represent the number 10 in decimal. We have 0 ones, and then we have 1 10, and so that makes 10 in decimal. 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, I've run out of symbols in my ones place, so I'm going to start over at 0, but then I'm going to increment the next place. So I'll start over at 0, and then the next place gets the next symbol, or 2, and that's how we represent the number 20. If we have 20 things, that's what we write, 2 and a 0. So in our number system, we can look at the number 4036. So if I look at place values, each place value is a power of 10, starting at 10 to the 0 power, which is 1, right? This represents the number of ones in the number. This is going to represent the number of tens. This will represent the number of 100s we have, and this will represent the number of 1000s. And if you notice, this is just 10 to the 0 power, 10 to the 1 power, 10 to the 2 power, 10 to the 3 power. So it just keeps going up in powers. And those are the different place values in our number. So if I have 4036, what that is saying is I have 4 1000s, and then I don't have any 100s, but I have 3 10s, and then I have 6 1s. So if you add those all up, you get 4036. That's how our number system works. In the binary system, it works exactly the same way. When we run out of symbols, we have to add 1 to the next place value. So I start out with 0, and then I go to the next symbol, which is 1. Now I've run out of symbols, right? So I'm going to have to start over, but then I'm going to add a 1 in the next place value. So I'll start out again with the 0, and then I have the 1, and then I'm going to go to the next symbol, which is 1. Now I've run out of symbols again, so I'm going to have to start over in the first place value and then the second place value, and then in the third place value I'm going to add a 1. And then this will go to the next symbol, and then I've run out of symbols, so the next place value will be a 1, and then I'm going to start over. So I can keep doing that pattern just like we do in decimal, right? And what that equals is those are the decimal equivalents from 0 to 10. So this is decimal 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So don't overthink it. It's just the representation that we're going to use to represent that many items. So if I want to say I have 4 chickens, I'm going to store it like this in the computer, okay? So in binary, each place value is a power of 2. Remember in decimal, each place value was a power of 10. But in binary, each place value is a power of 2. So we're going to start out with 2 to the 0, which is 1, and then 2 to the 1, which is 2, 2 to the 2 power, which is 4, 8, 16, 32, 64, and 128. Okay, and then it keeps going on and on. So on your flippy do, we found that if you turn those bits on, that's going to represent the number of that place, right? So if I have this binary number, this is saying that I have 128 plus 164. I don't have any 32s or any 16s, but I have an 8 and a 4, no 2s, and a 1. So if I add up all those numbers, I'm going to get 205. So this is the binary representation of how to store the number 205 in the computer. Okay, and so your flippy-do will help you with that. You can turn bits on and off, and then you just have to count up the values that are represented with a 1, meaning that place value is turned on. So let's see if we can find some patterns in binary numbers. So with 1 bit, we can represent 2 different numbers, right? If we only have 1 bit, we have 2 different numbers, 0 or 1. And with 1 bit, the biggest number we can represent is 1, right? That's the biggest. And then this is the number of numbers we can represent, and this is how many bits we have. Okay, so we have 1 bit, we can represent 2 numbers, and the biggest one is 1. So that looks like an interesting pattern. Let's see if that applies to other values of bits. So with 2 bits, we can represent 4 different numbers. We can have 0, 0, 0, 1, 1, 0, or 1, 1. Those are all the different patterns we can use with 2 bits. Okay, so let's look up at our table, and with 2 bits, we can represent 4 different numbers. And with 2 bits, the biggest number we can represent is 3. So if I take my 2 bits and they're both turned on and I add those numbers together, 2 plus 1 is 3. Okay, so that looks like an interesting pattern. It looks like the same kind of pattern that we just saw on the previous page. So maybe let's look at another aspect of this pattern. Well, it kind of looks like this number is 1 less than when I add these 2 numbers together. Okay, so 3 is definitely 1 less than 4. So let's try it again with 3 bits. So with 3 bits, we can represent 8 different numbers, right? We can arrange those 3 bits into 8 different patterns. So let's look at our pattern here. We have 3 bits. We have 8 different patterns. And those 3 bits, if we turn on all those 3 bits, the biggest number we can represent is 7. 4 plus 2 plus 1 is 7, right? And that happens to be 1 less than the 8. So it's the same exact pattern that we've seen 3 times. So let's see if we can use this same pattern to answer those questions using 6 bits. So the number of numbers we can represent, so if we're using 6 bits, would be 64. Okay, and the biggest number we could represent with the 6 bits would be 32 plus 16 plus 8 plus 4 plus 2 plus 1. So if we added up all those 6 bits, the biggest number would be 63. And that is one less than 64. So I think we found a pattern that we can use. And we are going to express this pattern using a formula which we will use the letter N to represent any number of bits. So I can say that what we've seen so far is the number of numbers is always 2 to the n. So if I had 6 bits, right, the number of numbers was 2 to the 6 or 64. So I can replace n with any number and figure out the number of numbers with that number of bits. So if I had 10 bits, the number of numbers would always be 2 to the 10th power. And I can replace n with any number to figure that out. And then the biggest that we've seen is always going to be one less than that number, right? So if I have 10 bits, it's going to be 2 to the 10th, and then I'm going to subtract 1. That's going to give me the biggest number. So you can see that we've kind of come up with a pattern by starting small and then adding bits along the way. So let's use this formula and see what we can come up with for 7 bits. How many numbers can 7 bits represent? Well, using our formula, we'll replace n with 7, and that gives us 2 to the 7, or 128. So 128 different numbers. And what's the biggest number? Well, it's going to be 128 minus 1, because if we add all of these 7 bits up, there's 1, 2, 3, 4, 5, 6, 7 bits. If we add up all of those numbers, it's going to equal 127, which is 1 less than 2 to the 7th. So now you try it. Figure out how many numbers can 10 bits represent, and then what is the biggest number that 10 bits can represent?